Okay, in this video we're going to be looking at finding the arc length of y equals e to the 1.9x plus e to the negative 1.9x all over 3.8 and then on the closed interval 0.5 to 1.9. And so we're going to practice some of the algebraic techniques that are used to find the arc length, because typically if we just pull out a random function and we say let's go ahead and find the arc length, and so of course I mean in a nice smooth random function, chances are the integration is going to not be very nice. So this one is rigged pretty nicely to work out. So in the arc length formula we have the 1 plus y prime squared under the radical, and so we're going to go ahead and work that through and kind of see what we got going on. So we need to find y prime, so it's going to be 1.9 e to the 1.9x minus negative 1.9 e to the negative 1.9x. Oops, that x is in the wrong spot. Okay, all over 3.8. Now factor out a 1.9 e to the 1.9x minus e to the negative 1.9x all over 3.8. 1.9 times 2 is 3.8, so we can divide by 1.9, and so that'll make the 1.9 in the numerator absorb, and 3.8 divided by 1.9 is 1 half. So we have 1 half e to the 1.9x minus e to the negative 1.9x. So when we do the 1 plus y prime squared, that's going to be 1 plus the 1 half e to the 1.9x minus e to the negative 1.9 x squared. Okay. All right. Now 4 over 4. 4 over 4 is 1. 4 over 4 is 1. That's the 1 at the front there. Okay. 1 half squared is 1/4. And then we're going to go ahead and FOIL e to the 1.9x minus e to the negative 1.9x. We're going to square that. So we're going to do e to the 1.9x times itself. So it's going to be e to the 3.8x. Remember, you add the exponents. Then you're going to have negative 2 e to the 1.9x times e to the minus 1.9x. So that's going to be negative 2 e to the 1.9x plus negative 1.9x. When we multiply like bases, we add the exponents. That's going to be negative 2 e to the 0, and e to the 0 is going to be just 1. And so we're going to get minus 2 as the middle term here as we are foiling this out. Okay. And then e to the negative 1.9x times itself. We're multiplying like basis. We're going to add those negative 1.9x's to get negative 3.8x. Okay. Now we have a common denominator here, so we can go ahead and add the like terms there. So 4 and a minus 2 is going to make a positive 2. So we have e to the 3.8x plus 2 plus e to the negative 3.8x all over 4. And that's going to go ahead and factor. Okay, so the 4 in the denominator can be written as 1 half squared. That's where we're going. E to the 3.8x plus 2 plus e to the negative 3.8x is a perfect square trinomial that factors into e to the 1.9x plus e to the negative 1.9x, and then all that quantity squared. And of course, you can spend some time and expand that out, and you'll see that it is the same. So this is really nice, because all of this under the radical is a perfect square, and so the square and the square root are going to undo each other, and then we will have a fairly easy integral. Okay, so 1 plus y prime squared is going to be 1 half e to the 1.9x plus e to the negative 1.9x, quantity squared, and then quantity square rooted, so the square and the square root will undo each other. Okay, and so that is our integrand. Okay, and we know what our limits of integration are. They're 0.5 to 1.9. So we're ready to go. We're ready to integrate this. We're past the hard part, which is the algebra. So the arc length is the integral from a to b, 1 plus y prime squared under the square root dx. It's going to be the integral from 0.5 to 1.9, 1 half e to the 1.9x plus e to the negative 1.9x dx. So that's going to be 1 half e to the 1.9x divided by 1.9 minus e to the negative 1.9x divided by negative 1.9. And so that's where we get that minus sign from. And we're going to evaluate this from 0.5 to 1.9. We can slide out the 1.9 in the denominator, so 2 times 1.9 is 3.8. Okay. And then we'll just go ahead and evaluate at the upper and the lower limits. Okay, so that's going to be approximately 9.1421 units after we throw that into our calculator. Okay, and then we'll go ahead and take a look at what the graph looks like. Okay, all right, so I have it in the graph there. So it's actually the hyperbolic cosine, which is cosh, C-O-S-H, and that's defined to be e to the x plus e to the negative x all over 2. And you may not have seen a little bit of this in Calculus 1. In the homework, you might see hyperbolic cosine. You don't have to use it as hyperbolic cosine. You could leave it as the e to the x plus e to the negative x all over 2. That is just fine. And our particular function, the cosh of 1.9x, is going to be equal to e to the 1.9x plus e to the negative 1.9x all over 2. So we don't quite have that because remember ours had a, what did it have, a 3.8 on the bottom. So if we go ahead and divide this by 1.9, and then 1.9 times 2 is going to be the 3.8. And so that's what we originally had. So e to the 1.9x plus e to the negative 1.9x all over 3.8. That's really cosh of 1.9x all over 1.9. Okay. Now, I'm going to kind of do like the last examples I did is I'm just going to take the two endpoints and I'm going to find the distance between those two endpoints, and that can kind of give us a reasonable estimate of, well, I don't know if it's necessarily reasonable, but we can kind of compare it with the actual arc length and see how close they were. And maybe you can use that to kind of see if you have a reasonable arc length. All right, so we're going to find the distance between those 2 points. So 1.9 minus 0.5 squared plus 9.735 minus 0.782 squared. That's going to be approximately 9.061. So it is a little bit shorter, and that'll be the case if you use the endpoints. It's most likely going to be a little bit shorter. Again, I would say this. So we're finding, the length of this line segment here, and so that part of the parabola it's not a parabola, but it looks like a parabola. It looks fairly straight, and so using the endpoints, I would say, would give us a decent approximation. And so let's see, we have 9.0618 is our guesstimate. The actual was 9.1421, and so it's decently close. As just a means of, okay, are we even in the ballpark with our arc length integral, and so this certainly is a good estimate. Okay, so this was the last example of the arc length. I think there might be one other technique. I might have another video of that other technique. It's just an algebraic technique for some of these arc length problems that are rigged so that you have a little bit of variety of doing arc length where it's not an integral that you're not able to integrate by the methods that we currently have. Okay, so the next video is going to be on the surface of revolution. So we'll see you next time.